Class 11th Chemistry, Unit 4 Chemical Bonding and Molecular Structure, and in this video we will discuss about bond parameters like bond length, bond angle, bond enthalpy and bond order. First come to bond length. Bond length is defined as the equilibrium distance between the nuclei of two bonded atoms in a molecule. Bond lengths are measured by spectroscopic, X-ray diffraction and electron diffraction techniques. Each atom of the bonded pair contributes to the bond length. In this diagram, you can see this is the one molecule is there. A atom and B atom both are bonded in this. And the distance from nucleus of this to this one, this is called bond length. Okay, and in this bond length, this RA represent the contribution of this atom A. Okay, and this RB represent the contribution from this atom B. In the case of a covalent bond, the contribution from each atom is called the covalent radius of that atom. Okay. Now let us see what is covalent radius and van der Waals radius. The covalent radius is half of the distance between two similar atoms joined by a covalent bond in the same molecule, and the van der Waals radius is half of the distance between two similar atoms which are not bonded. This is a one chlorine molecule. In this, two chlorine atoms are bonded. Okay, and this is one chlorine molecule and this is another chlorine molecule. Now, if we consider this atom and this atom of chlorine, these are not bonded to each other. Okay, that's why again if we compare, these are the two bonded atoms and distance from this nucleus to this nucleus, this is called bond length, and this is 198 picometer, or this is also known as the internuclear distance between bonded atoms, and half of it, this one, this is called covalent radius. Now if we consider the nucleus of this atom and the nucleus of this atom, this distance, this is again internuclear distance, but in this case atoms are not bonded, and half of it, this one, this is called covalent radius. Sorry, this is called van der Waals radius. Now from this diagram you can clearly see that van der Waals radius is always greater than covalent radius. Okay. Next bond parameter is bond angle. It is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or complex ion. Bond angle is expressed in degree, which can be experimentally determined by spectroscopic methods. It helps in determining the shape of molecule or complex ion. For example, HOH bond angle in water is 104.5 degree. You can see this is the structure or shape of water molecule. This is HOH bond angle and this. And from this structure you can say water molecule is bent in shape. Okay. Next bond parameter is bond enthalpy. It is defined as the amount of energy required to break 1 mole of bonds of a particular type between two atoms in a gaseous state. The unit of bond enthalpy is kilojoule per mole. Now, for example, this is H2 molecule is there And if this H2 molecule, which is present in the gaseous state, dissociate into atoms, which again present in the gaseous state, then whatever the heat we are supplying, that is known as bond enthalpy of H bond in H2. Okay. Another example is O2. In O2, two oxygen atoms are joined by a double bond. Okay. And whatever the heat we are supplying to dissociate this O2 gas molecule into oxygen atoms in gaseous state, then this energy is known as bond enthalpy for oxygen bond in O2 molecule. The same way, in case of nitrogen, triple bond is there between nitrogen atoms, and whatever the heat we are supplying to dissociate these atoms, to dissociate this nitrogen molecule into nitrogen atoms in gaseous state, then that enthalpy or heat is known as bond enthalpy of N bond in N2 molecule. Okay. Larger the bond dissociation enthalpy, stronger will be the bond in the molecule. Now you can compare. If you compare these three values of bond enthalpy, for nitrogen this is highest. That's why we can see the triple bond between nitrogen is stronger. Okay. And in this process again you can see the products are in the atomic form. These are in atomic form. That's why this bond enthalpy is also known as enthalpy of atomization. Clear? In case of polyatomic molecules like water, H2O. Now, in case of H2O, we already discussed its shape. This is H2O. Now, in H2O, there are two OH bond. This is one OH bond and this is another OH bond. And these two OH bonds broken down in steps. In first step you see this H2O will dissociate H2O in gaseous state. Remember it. It dissociate to give H gas and OH gas. And in this case bond enthalpy is 502 kilojoule per mole. And now this OH gas will dissociate to give H gas and O gas. And in this, the bond enthalpy is 427 kilojoule per mole. You can see both are different. Two OH bonds have different values of bond enthalpy because of changed chemical environment. Okay. Actually, in this molecule, this hydrogen atom is there. This is bonded to this oxygen, and this oxygen is bonded to this hydrogen. But in this hydrogen is directly bonded to the one oxygen atom. That's why their chemical environment in both these species is different. That's why we will get the two different values for OH bond. Therefore, in polyatomic molecules, the term mean or average bond enthalpy is used. Then how can we find out this average bond enthalpy? It is obtained by dividing total bond dissociation enthalpy by the number of bonds broken. Average bond enthalpy of OH bond in water is calculated like this. This is 502 plus 427 divided by 2, and this will come 464.5 kilojoule per mole. Okay. Next bond parameter is bond order. In the Lewis description of covalent bond, the bond order is given by the number of bonds between two atoms in a molecule. For example, hydrogen molecule. There is one shared electron pair. Number of covalent bond is 1. That's why bond order is also 1. In case of oxygen molecule, two pairs of electrons are shared. Number of covalent bonds are 2. That's why bond order is also 2. In case of nitrogen molecule, number of shared electron pairs 3. That's why number of covalent bonds 3 and bond order is also 3. Carbon monoxide CO. Number of shared electron pairs 3. Number of covalent bonds 3. Therefore bond order is also 3. In case of isoelectronic molecules and ions, I think you know that what is the meaning of this isoelectronic molecules and ions. That is, molecules and ions have the same number of electrons, have identical bond orders. That is, same bond orders. For example, F2 and O2 2 minus have bond order 1. In this O2 2 minus, this is known as peroxide ion. Now, if you find out the number of electrons in this one and this one, in case of F2, each fluorine atom has 9 electrons. That's why total number of electrons in F2 is 18. Now, in case of O2 2 minus, there is 2 oxygen atom. Each oxygen atom has 8 electrons. Plus, there is a 2 negative charge. It means 2 electrons are extra. If you add it, again you will get the 18. One more example. N2CO and NO plus have bond order 3. All these 3 species are isoelectronic species. And in this case, NO plus is known as nitrosonium ion.
Relation between bond order, bond enthalpy and bond length. With increase in bond order, bond enthalpy increases and bond length decreases. Again, remember it. With increase in bond order, bond enthalpy increases and bond length decreases. We can say bond length is inversely proportional to bond order. Smaller the bond order, okay, smaller the bond order, larger the bond length. And bond length is directly proportional to bond order. Higher the bond order, more amount of energy is required to break that bond. That's why bond enthalpy is larger. Bond enthalpy is inversely proportional to bond length. Okay, shorter the bond length, larger is the bond enthalpy. Is it clear? Thank you. Subscribe my channel to get the new videos.